In this lecture, we will discuss catalytic metathesis. Metathesis, as we had discussed in the last lecture, it is a change in place, and in the case of olefins, when you have alkylidine groups and if alkylidine groups change places, then you would have a metathesis reaction. In the slide that is there before you, you will notice that two alkenes and they are the same alkene AB, which is basically indicative of two alkylidine groups joined together. If we do a metathesis of this AB olefin, then you can get both AA and BB, and if you remember, this allows for a change in the size of the olefin. So, if you take a small olefin and you do metathesis, you can get a bigger olefin and a smaller olefin, and this is very useful for the petroleum industry. In fact, metathesis was originally discovered in the industry, and eventually it was understood better through the work of Chauvin, and he discovered what is called the non-pairwise mechanism for the metathesis. We will just briefly revise what we have discussed earlier, and I have before me a set of 4 olefins, which are represented by these green, magenta, blue and black alkylidine groups. And the alkylidine groups that are going to be exchanged are the ones which are shown in round as a round figure, and the alkylidine groups which are stationary or will remain in the same place are the ones which are in square shape. And so, you will notice that if you take 4 different olefins, you can have a complete random distribution of these olefins. The gray round figure, which is attached to the metal, which is basically having M double bond CH2 here, is going to be exchanged with the green one to start with, and then the green alkylidine group is exchanged with the magenta, and the magenta is exchanged with the one on the trans position. So, you will notice that the round magenta has gone here, the green one has come here, and the blue which was here has come over to this position. So, this is just to indicate that you can have a completely random distribution of the alkylidine groups. This non-pairwise mechanism was suggested by Chauvin, and you will recollect that Chauvin got the Nobel Prize in 2005 for this very reason, for discovering the actual mechanism that was behind this famous metathesis reaction. Pictured here is the mechanism. You start with MCH2, M double bond CH2, and then you can exchange it with another olefin in such a way that you can eliminate ethylene, and that is what is happening here. Ethylene is eliminated and a new alkylidine metal system is generated, which can interchange with another alkylidine group of another olefin in order to finally generate a completely new olefin. So, these are the two products. This is product 1 and this is product 2. And these two olefins are generated starting with 2 olefins, which is the reactant 1 and reactant 2. This is reactant 1 and this is reactant 2. So, based on this type of a non-pairwise mechanism, it was possible to explain all the reactions that were observed in the metathesis reaction. So, what we have not discussed in the last lecture, where we discussed the mechanism of this process, is the fact that the catalysts required for metathesis were often very complex. Originally, it was discovered by Standard Oil Company and patented also by Phillips Petroleum for a specific case. And most of these companies used very complex mixtures for carrying out metathesis. In general, it could be said that a early high oxidation state metal ion or a metal complex, an oxide or a chloride was used, and this was followed by a reducing agent. So, a high oxidation state metal. So, this is the high oxidation state metal that I am talking about, and then this was combined with a reducing agent. Very often this was an aluminum alkyl species, aluminum alkyl or aluminum alkyl chloride, and then surprisingly small amounts of ethanol or water were required in order to initiate the reaction. There were several disadvantages for this particular mixture. One was the fact that the catalytic species was not known. It could be a variety of different species which were generated starting from this mixture. So, the catalytic species itself could not be modified. It was an unknown species, and there was very often an initiation period that was required in order to start the reaction, and so the reactions were slow to begin with before they took off. This means that the reaction itself would lead to, in terms of when you have reactions which lead to polymers, you have a large range in the molecular weight. We will talk about this a little later on during the course of this lecture also. So, this is a big disadvantage, but nevertheless the petroleum companies found it extremely useful to do metathesis reaction in order to generate more useful fractions from the petroleum fractions that were isolated directly from the crude, So, it was a useful reaction, but then the catalyst was not known. After Chauvin unraveled the mechanism of the reaction, it was clear that one needed a carbene, and so this carbene catalyst was used, or was one of the first ones which was rationally designed. And you will notice that this carbene species was the catalyst, but it was still in a high oxidation state, and it required an aluminum alkyl species, aluminum halide, in order to activate the species. So, a Lewis acid was apparently, for some reason, it was required in order to carry out this reaction forward, and this Lewis acid activation is presumably to generate a vacant coordination site on the tungsten. So, this was better than complex mixtures. The complex mixtures that were originally known for carrying out metathesis reactions were extremely complex. This was better, it was 2 component, but still it was not as good as what one would desire. So, the first breakthrough came from the work of Schrock and Grubb. We will discuss these two in detail. We will take up the Grubb's catalyst first, and then we will talk about the Schrock's catalyst. Grubb's catalyst was a modification of the carbene systems that were known, which were derived from Fischer carbenes. Fischer carbenes were those species where you had a late transition metal along with a carbon bearing a heteroatom. However, when you replace the heteroatom with all alkyl groups, the carbene became lot more reactive, and especially reactive towards the metathesis reaction itself. And so, this catalyst, which was first made by Grubbs, which is called the first generation catalyst of from the Grubbs group, is extremely important for several reasons. First of all, it was the first single component catalyst, which means that it did not require another species in order to initiate the reaction. Secondly, it was the precursor for several other second generation and third generation Grubbs catalysts. This is also important, and the fact that it could be easily generated, and the reaction that and the reaction that is used for making this complex is shown here. In fact, RuCl2 PPH3 thrice is the starting material, and this starting material can now be reacted with a diazocarbene precursor, and this leads to transfer of the carbene to the ruthenium, and this molecule is a stable molecule which can be isolated and characterized. This species, which is generated by attaching a carbene to the RuCl2 PPH3 thrice, turns out to be less reactive. It is not as good a metathesis catalyst, but when you replace the triphenylphosphine with tricyclohexylphosphine with a simple substitution reaction, you end up with the first generation catalyst. This is the first generation catalyst from the Grubbs group, and it turns out to be a good metathesis catalyst. So, there are advantages for this catalyst system. First of all, it can be readily synthesized, very easily synthesized in the laboratory. It is a stable system which can be stored and used again and again without difficulty. You do not have to make it fresh every time you want to do the reaction. So, this is the primary advantage, and it is a single component catalyst, and as I said, that is the major advantage of the Grubbs catalyst. Now, after Grubbs declared the synthesis of this catalyst, it turns out that several people wanted to make better metathesis catalysts, something that would be more reactive than the first generation catalyst, which could not be used with several substrates. And three people, Nolan, Grubbs and Fusner, discovered that if you can attach N-heterocyclic carbene, this is a N-heterocyclic carbene which we have encountered earlier. If we can attach a N-heterocyclic carbene to the ruthenium, replacing one tricyclohexylphosphine on the ruthenium with a carbene, then the catalyst turns out to be much more reactive, much more useful, and presumably the electron density on the ruthenium is increased, and it is also true that you have large aryl groups which protect the ruthenium center from unnecessary reactions and decomposition. Now, all three of them published this about the same time, but following this initial result, Grubbs showed that if you replace the unsaturated N-heterocyclic carbene in the present system, you have an unsaturated heterocyclic carbene, and if you replace it with a saturated variety of N-heterocyclic carbene, then it turns out that the reaction is much better, and the variety that Grubbs made actually had simple methyl groups to protect the aryl, to give steric protection to the ruthenium, and you have a stable ruthenium complex. And in fact, you, for the sake of our understanding, we will convert that single bond into a double bond, because we normally talk of this as a carbene, and the carbene coordination to the ruthenium is the one that promotes the reactivity of this center. During the course of this reaction, it is usually PCY3 which leaves and generates a vacant coordination site on the ruthenium. In general, if you want a catalyst to function in the resting state, you would have a ligand, an extra ligand which leaves and generates a vacant coordination site which initiates the reaction. Grubbs published the synthesis of this compound and its reactivity just a few months after he had published the unsaturated variety, but it was very clear that the unsaturated variety was the most active form, and so it became what was called popularly as a second generation Grubbs catalyst. The second generation Grubbs catalyst turns out to be a lot more reactive, stable and useful for carrying out metathesis reactions. Now, during the course of this study, there were other attempts to modify the N-heterocyclic carbene in such a way that it would give you a system which would generate a very reactive catalyst. And this time mention should be made about the Hoveyda-Grubbs catalyst. This was a combination of the Grubbs catalyst system. Basically, you had an N-heterocyclic carbene, which was saturated variety, and you also had a carbene which was the essential reactive component of the metathesis catalyst, but the PCY3 was replaced. The PCY3 was replaced with a pendant group on the alkylidene, such that it coordinated to the ruthenium and blocked that site. So, the vacant coordination site at the ruthenium was very readily generated by loss of this RUO bond. So, this RUO bond was lost initially, and that led to a reactive form of the catalyst. Now, this turns out to be a little more useful. It is less reactive, but it is more stable because of the internal coordination of the alkylidene. So, when you design a catalyst, it is very important that you design a catalyst that is as reactive as possible, but at the same time it has a long shelf life, and that is what we consider by more stability. However, these two things are very often working at cross purposes, because if you make the complex very stable, then it will be less reactive. So, let us proceed further. After Hoveyda made this modification for the Grubbs catalyst, the Grubbs second generation catalyst was the one which was most useful, but it was not very reactive. And Grubbs showed that if you replace the pendant group with a pyridine unit, a substituted pyridine, and if you react the Grubbs second generation catalyst with pyridine, specifically bromopyridine, then it turned out to be an extremely useful catalyst. It was extremely reactive. In fact, it initiates metathesis a million times faster than the second generation catalyst. This, like I said earlier, it turns out to be an extremely important fact for polymerization. If you do polymerization, metathesis polymerization, which we will talk about in a few minutes, if you do metathesis polymerization and if there is a long initiation time for the catalyst to start functioning, then you will end up with polymers with a variety polydispersity which is undesirable. So, it is important to have as low a polydispersity as possible. That means, the molecular weight range is very small. Then you get much better polymers with better physical characteristics, and so it is important to have a catalyst which is extremely fast, which has no lag time for the initiation of the reaction. So, this catalyst, which is called the third generation catalyst, is an extremely fast catalyst, which initiates metathesis a million times faster than the second generation catalyst. So, now we let us take a look at for Schrock's design. Schrock was a person who was working with early transition metals and high oxidation state carbene compounds. If you remember, the metathesis catalysts that were initially designed that were known in the patents were all early transition metals, oxides or chlorides, which were activated with an alkylating agent, either a tin R4 tin compound, or it was an AlR3 compound, something that would alkylate early transition metal. So, Schrock's design is quite natural. It starts with a molybdenum species, which is there in the high oxidation state, and he showed that if you take a carbene, a Schrock carbene, which surprisingly has no heteroatom to stabilize it. If you take the Schrock carbene and if you attach two alkoxide units, then it can function as a metathesis catalyst. But surprisingly, the alkoxy groups which are attached to the metal have to bear some electron withdrawing groups. if they are not electron withdrawing, then they are not as reactive as one would like them to be. So, the Schrock's catalyst, the most celebrated form of the Schrock's catalyst is what I have shown here. This has got 2 trifluoromethyl groups attached to the tertiary butoxy unit that is attached to the molybdenum. So, this is a Schrock catalyst, which turns out to be the most useful form of the catalyst. It has got an alkylidene group. So, M double bond CH2 is still the basic unit, which is the catalytically active unit for metathesis, and that remains common for both Grubb's catalyst and Schrock's catalyst. The only difference is the fact that the molybdenum catalyst, that is the basis for the Schrock's catalyst, has got 2 alkoxy groups, which are electron withdrawing in nature. Now, Schrock's catalyst also had another advantage, and that advantage is shown here, and that is the fact that you can generate a chiral Schrock catalyst. Now, if you remember, the catalyst center has got 2 alkoxy units, and binol, which is got an axially chiral, it is an axially chiral molecule, which means that there is no single carbon which bears a asymmetric unit. The chirality comes from the fact that you cannot rotate these molecules around this carbon-carbon bond very easily, and so the chirality resides in the fact that these 2 planar rings are oriented in such a way that they have a helical axis to them. So, now you have 2 alkoxy groups. This is the binol unit, which is attached to the molybdenum, and it bears a chirality at the molybdenum. And now, if you can do a catalysis, metathesis catalysis using this alkylidene unit, the molybdenum center, which is carrying out metathesis, always has a chiral center. And so, whenever you have the possibility for generating some stereo selective carbon-carbon bond formation, then it would be possible to do it in a selective way when you have this chirality or this handedness on the molybdenum center. So, the Grubb's catalysts at the moment, at least the ones that I have shown you, do not have the chirality inbuilt in them, whereas the Schrock's chiral catalyst has this major advantage in that there is a chiral center which is attached to the molybdenum and which is retained right through the reaction, and so it turns out to be an extremely useful center for inducing chirality. So, let us see how these systems are being used. So, we have discussed the catalysts in detail, but in all the cases it is only the M double bond CH2 that is really important for carrying out the reaction. So, it is only the M double bond CH2 that is a catalytically active center, and whatever we have described, the rest of the paraphernalia that is attached to the metal purely provides assistance in terms of stabilizing the molecule, stabilizing the catalyst, or providing the right electronic input into the metal, so that the catalysis can be carried out. So, let us go to the actual examples where reactions can be carried out. I would call self metathesis as a first example. Suppose you just have two alkylidene groups which are identical, and you carry out metathesis, you would end up with reactants and products which are the same. I would call this self metathesis, and there is no thermodynamic loss or gain in this whole process, and there is no effective reaction also. So, it is not of a great utility to have the self metathesis. So, the more useful reaction is the one where you have cross metathesis. Now, let us imagine the extreme scenario where you have 4 different alkylidene groups attached to the olefin. So, in other words, 2 olefins are undergoing metathesis and there are 4 different alkylidene groups. I have labeled them as A, B, C, D, which means A is one alkylidene group, B is a different alkylidene group. Similarly, C, D is a different olefin. Now, you just imagine the metathesis reaction carried out in this case will lead to almost 10 different olefins, because the alkylidine groups, unless they have very strong electron withdrawing or donor groups on them, you will not have a major difference in the delta H of this reaction, and it goes from left to right after metathesis. So, if you have AA, AB, AC and AD, there are 4 different olefins that can be generated, starting with the alkylidine group, which is A, attached to the alkene, and then it is transferred to the metal, and then it can be transferred to any one of the other olefins. Similarly, you can write out the remaining number of olefins that can be generated with each one of these alkylidines, and you will realize that there are 10 of them. So, 10 different alkenes can be generated. In the event that the alkylidine is symmetrical, you will have only 10. If you have an unsymmetrical alkylidine group, which means that you have, let us say, CH3CH group. So, if the alkylidine, for example, has got this type, this is the alkylidine group that we are talking about, then you can have both cis and trans olefins generated from this alkylidine. So, a maximum of 20 alkenes can be generated, just starting with 2 alkenes and 4 alkylidine groups. This is the maximum that can be generated, starting with 4 different alkylidine groups. So, now let us take a look at how one can utilize such a reaction, which leads to a complex mixture of 10 alkenes or 20 stereoisomers. How can that be of any use? So, this is something that we need to consider. Very often the cross metathesis reaction, which is what we are talking about when you have different alkylidine groups, is designed in such a way that it will give us only the product which is of importance, and the other product is conveniently eliminated from the reaction mixture, either because it is volatile or in such a way that it can be isolated very easily. So, let us take a look at this reaction, which I have indicated here, whether it is cis or trans alkene. If you can combine it with ethylene, let us say, and carry out a metathesis reaction. I have indicated the metathesis catalyst as alkylidine as a carbene, metal carbene unit. In principle, it can be either a Schrock catalyst or a Grubbs catalyst, but in this in the case of olefins, very often it is convenient to just take the more readily available and the less air sensitive Grubbs catalyst and carry out the reaction, and one will end up with these 2 alkenes during the course of this reaction. If you want to control this reaction in such a way that I want to make only the alkylidine, only the alkene which is pictured here, I can push this reaction to the left very simply by allowing the ethylene to escape from the reaction mixture. So, the Le Chatelier's principle will be operating, and one would go from the right side of this reaction to the left side, and ethylene would be allowed to escape. Suppose I want to split a very large olefin, which has got say C18 olefin, which has got the double bond in the middle, and I want to convert it into 2 olefins which are smaller in size, then I can just have a high pressure of olefin. So, if I control the concentration of ethylene, I can move the reaction from left to right. If I increase the ethylene concentration, I can very simply make the smaller olefins and move the reaction from left to right. So, this turns out to be a useful way of controlling the metathesis using the Le Chatelier's principle. It is also known that there are some electronic factors which control the reaction. Here I have shown an example where I have an electron withdrawing group on the olefin, in which case then the reaction turns out to be useful if I have more amount of this electron withdrawing group attached olefin, which is marked as this aldehyde, the substituted butyraldehyde here, and that is taken in a slightly larger amount. And you will notice that this can again end up with elimination of the 2 CH2 groups, and ethylene is eliminated during the course of this reaction. And very conveniently, you have generated a useful aldehyde, which is now having a much larger molecular weight. And you will also notice that although you had a unsymmetrical alkylidene group. So, in other words, this alkylidene would end up with both cis and trans. You will notice that this reaction mixture ended up with the E by Z ratio. That means, the trans compound, the trans product was formed in a ratio of 20:1 for the cis compound. So, this turns out to be a very easy way of generating, starting with, here I have shown this reaction was done with the Grubbs second generation catalyst, and you ended up with a 92% yield just by adding 2 equivalents of the aldehyde that you started out with, and you ended up with an aldehyde which was more useful and in 92% yield. So, this was carried out with Grubbs second generation catalyst, and it allows for a reaction where you have an aldehyde as a substituent. Now, a similar reaction with a modified Grubbs second generation catalyst, here again you get an silyl substituted alkene, and this can also proceed from one side to the other side purely by removal of ethylene from the reaction mixture, and you end up with as 81% yield of the desired product and a E by Z ratio of 11. So, in all these cases, ethylene, the amount of ethylene that was used was amount of ethylene that was removed from the reaction mixture was the key for pushing the reaction from left to right and generating the product that was useful. So, here I have shown you another example where you ended up with a useful product 80% yield, again with Grubbs first generation catalyst. It is only 5 mole percent of the first generation catalyst, very mild conditions. You can convert the compound which is of use. In this particular case, it is the side product is a product that is reasonably volatile and can be removed from the reaction mixture. So, you can see that Le Chatelier's principle is the key for generating useful products. So, you can also have some steric effects during the course of this reaction. Now, you will remember that olefins have a tendency to coordinate to metal atoms to a lesser extent when they are substituted. So, since the olefin has to be coordinated to the metal during the course of the reaction works well when you have less substituted olefins. Here I have shown you the first step in the whole metathesis process, and that is the formation of the elimination of the alkylidene group which is attached to the ruthenium center on reaction with the starting material. So, here I have biased the reaction in such a way that I end up with only the substitution, initial substitution of the alkylidene group on the ruthenium. So, if you look at the rates of these reactions, at the rate at which the reaction proceeds, this reaction proceeds from left to right, you notice that if I have a single substituent on the ethylene, so that is the fastest, that proceeds at the rate of say 100 arbitrary units. Then the moment you have 2 substituents on the olefin in a cis position, then the reaction slows down by almost 10 orders of 1 order of magnitude. It comes down to 10 relative units. And similarly, if you have a heavily substituted alkene and if you have a trans substituted alkene, then the reaction falls by another factor of 2. So, you can see how the reaction goes slower and slower as you have greater and greater number of substituents, and the cis substitution pattern is better than the trans substitution pattern. And this turns out that if you have a heavily substituted olefin, especially one with a phenyl group. So, if you have a styrene, then the reaction is practically virtually non-existent with when you have the Grubbs first generation catalyst. So, this gives you an idea about how it is important to have very reactive olefins, and if you want to carry out the reaction in a fast manner. So, there are various ways which allow you to control the reaction, and these are used very effectively for doing cross metathesis. Now, we come to a special class of reaction which is called ring closing metathesis reaction. The ring closing metathesis reaction is a special case when the two olefins which are undergoing metathesis belong to the same molecule. So, if I have two double bonds which are positioned in such a way that you can eliminate two alkylidene groups and form a ring. So, basically what we are doing in this particular case is we are eliminating these two CH2 groups. We are eliminating these two CH2 groups and forming ethylene. And as I told you earlier, elimination of ethylene is very often a convenient way of pushing the reaction from one direction to the other direction. So, this itself drives this, because ethylene is a volatile species which can be eliminated from the reaction mixture. More than that, the reaction is entropically favored by having the two groups which are joining together form a single molecule. So, in other words, two different olefins are not formed, a single olefin is formed, and that leads to a 5-membered ring which is entropically very favorable. This is a 5-membered ring which is formed, and the new bond that is formed in between these two carbons turns out to be a very favorable situation. So, Grubbs first generation catalyst is convenient for carrying out these type of reactions, and you will notice that E is actually electron withdrawing group, and very often it is COOET or COOMe, and this you will recognize as a species which is coming from a dialkylation of diethyl malonate. So, if you take CH2, COOMe, dimethyl malonate, and you alkylate this active carbon, then you will end up with this particular starting material, and it is a very convenient starting material, and you can generate this 5-membered ring very readily using a ring closing metathesis reaction. This turns out to be useful, and it can even be done with a larger sized ring, not necessarily with a 5-membered ring. And once again, Le Chatelier's principle is utilized, so that you can remove ethylene and form a very nice ring system. Let us take a look at the mechanism of the ring closing metathesis. Why is it that it is so convenient to carry out the metathesis reaction? I have color coded the alkylidene group which is present on the ruthenium to start with, and you will notice that the replacement of this PCY3 on the ruthenium with the olefin from the starting material or the reactant led to a ruthenium alkylidene alkene complex. This is a key intermediate. Now, starting with a ruthenium 2 center, you end up with formally a ruthenium 4 center. Here you carried out what we call as a oxidative coupling reaction, where the ruthenium undergoes formal oxidation and you have coupled two carbon centers. Basically, the two carbon centers which are coupled are marked here in the dotted lines, and so you end up with a new bond which is a metallocyclobutane. A ruthenium metallocyclobutane is formed, and this ruthenium metallocyclobutane can now break in a different fashion. Earlier you had the formation of a new carbon-carbon bond between the CH2 group which was coming from this starting material and the alkylidene group which is present on the metal. Now, I can eliminate this alkene. I can eliminate this alkene and I shall show it in a different color, so that you can follow it very easily. I break these 2 bonds and form a new carbon-carbon double bond. If I form a new carbon-carbon double bond, then I end up with this product is eliminated and I have an alkylidene group, where the starting material is now coordinated to the ruthenium. I have an alkylidene group which can now carry out another metathesis reaction, now with this olefin which is attached to the same molecule. So, an alkylidene group which has got an alkene inside as an internal reactant turns out to be a very fast reaction, and that is what we have written here. Now, we move this CH2 double bond to this position. If you move it to this position, then you end up with a cyclic intermediate, and this cyclic intermediate once again forms a bond. This time the ruthenium carbon bond is formed here and the carbon-carbon bond is formed here, the new carbon-carbon bond. The metal now again goes from +2 to +4 oxidation state, and this can now eliminate, can break in such a way that you form RuCH2 as the final as a catalyst, again as a regenerated catalyst, and the cyclic product which is listed here. So, we can write these 2 systems together. Now, I will start with the RuCH2 which I generated in the previous reactant step, and now we can go through the catalytic cycle fast. You have the formation of a metallocyclobutane which is listed here, and it can eliminate a cyclopentene which regenerates the catalytically active intermediate. So, this is the mechanism of the ring closing metathesis. This is the mechanism of the ring closing metathesis. Now, you will notice that the same reaction can be pushed in the opposite direction if you have a large amount of ethylene. Suppose I have a high concentration of ethylene. If I have a high concentration of ethylene and I take the ring closed product, then I can have a ring opening metathesis. So, this is called ROM, the previous one is called RCM, and this one is called ROM, ROM, and the ring opening metathesis can push the reaction from the ring closed system to the ring open system. Now, exactly the same reaction can go back, the same steps can be retraced in order to generate this product. In this particular instance, this is the product. So, you can note, you realize how the reaction can be used to very effectively go from one direction to the other direction in a very effective fashion to generate a wide variety of starting materials and products. So, once again I can take the reactant which I had shown you earlier, which is the diethyl malonate which has been alkylated, dialkylated using 2 allyl groups, and that again is an easy step. If I take these 2 diallylated species, I can in fact eliminate ethylene once again from 2 different molecules. Now, that will lead to a new diene. This time it will be actually a triene. It is a triene because you have generated a new double bond in the process. So, 2 dienes come together and form a triene, and now you will realize that you can keep adding these molecules together in such a fashion that you can form a polymer. So, I can remove 2 CH2 units from one of these molecules and another one of the starting material and lead to a polymer. So, this is a polymerization reaction which is executed through metathesis, and in each step ethylene is eliminated, and because ethylene is a volatile molecule that can be quickly removed from the reaction mixture, and you can have a very efficient way of polymerizing a diene. So, this is called acyclic diene metathesis polymerization. Acyclic diene metathesis polymerization is a system where you eliminate ethylene from a diene molecule in such a way that you form a polymeric molecule. How do you push the reaction? The same reactant has been used for 3 different reasons. One is to do ring opening metathesis, another is to do ring closing metathesis, another is to do acyclic diene metathesis polymerization. So, here the concentration of the diene is a key. Concentration of the diene, if it is very high, then the polymerization results, and if you remove ethylene during the process, then you can very effectively make a large high molecular weight polymer starting with an acyclic diene. Now, if you add a lot of ethylene to a cyclized product, then of course, you can go from the ring closed product to the ring open product. So, you can push the reaction in different directions based on the concentration of the reactant which is there. Polymerization is a competing process whenever you do ring closing metathesis polymerization or a ring opening metathesis polymerization. So, the lower concentration always prevents polymerization. If you have a large amount of the diene, large concentration of the diene, then the possibility of the diene reacting with itself is higher, and that of course, leads to polymerization. If you have high temperature, then the ring opening and the elimination of ethylene is promoted, because delta S, T delta S increases in the process, and you can have larger free energy change, negative free energy change as a result of the reaction. And so, that would be a more favorable process when you have the reaction proceeding in a forward direction. That means, you have ring closing during the whole system. If you remove ethylene, of course, you want to if you want to do ring closing reaction, you should remove ethylene from the reaction mixture, so that it does not come back and compete for the reaction. So, you can see that how this particular metathesis reaction is extremely useful, and it has been used extensively for the synthesis of a variety of natural products. And the natural product synthesis especially for unusual ring systems has been conveniently accomplished using the metathesis catalysis. Here the Schrock catalyst has been used very effectively. You have 2 reactive groups, you have an amide functionality which is present here, and you have ether functionality, and in the presence of these functionalities, if you want to do a metathesis reaction, it is convenient to do it with the Schrock catalyst, and the Schrock catalyst carries out this whole reaction in 25% in 98% yield. And if you but you need a large amount of the catalyst for this whole process to function. But nevertheless, this is a very efficient way of making such a large ring natural product, and very effectively you can generate the ring system. And a recent synthesis of another natural product, manzamine A, which has been isolated from a marine organism, is shown here. This was accomplished by a ring closing metathesis in the presence of very labile functional groups. This is a very complex natural product with so many ring systems, and in spite of all that, the reaction could be carried out, and Fukuyama and the co-workers have recently published the total synthesis of such a complex natural product. The last step is the ring closing metathesis, which was accomplished, which led to the generation of this chiral natural product being synthesized very efficiently. So, with this, I would like to end today's lecture. I will show you some of the key options. So, we will summarize today's lecture by saying that Metathesis requires a carbene complex. It can also be carried out with a carbene complex with acetylenes. We have not discussed this in today's lecture, but it is also possible. The most important point to note is the fact that there is non-pairwise exchange, and this non-pairwise exchange means that you will have a plethora of products in this whole reaction. And in order to carry out this reaction effectively, you need to utilize thermodynamics to the hilt. So, if you have to use Le Chatelier's principle, that is the most important principle that can be used to advantage in order to push the reaction in the direction in which you want to carry out the whole, push the reaction from the reactant to the product side. You have to utilize Le Chatelier's principle very effectively. Temperature and concentration also are important when you have to carry out polymerization reactions. You can utilize the whole thing with efficiently when you use if you use high temperatures, then T delta S is large, and so you can push the reaction to the side in which you want to carry out the reaction efficiently. So, it is the metathesis reaction, although it seems to be such a non-specific reaction, it generates a large number of products very easily. You can use it very effectively if you remember that the importance of thermodynamics. If you remember the importance of thermodynamics, you can push it in the direction in which you want it to proceed. So, in the case of carbynes, you can use the reaction with acetylenes and you can generate metathesis of carbynes, and that leads to acetylenes, polyacetylenes, which are very difficult to make otherwise, and you can make very interesting materials, which we shall cover in a future talk.